Hi, welcome to the Olympiad geometry. Let's continue our study. Before we start, if you think this video is helpful, please click the like button, comment, share, and subscribe to the channel. So some of the audience maybe already get bored with basic stuff, but I think the basic stuff is very critical. And I received this problem from the audience. First, I need to say sorry for the audience because I was extremely busy with my job recent 2 weeks. So I didn't check the email, and I checked this email tonight. I found this problem, and I think this is a very interesting problem. So I try to solve it, and I think this is a problem close to the modern MMO level. Anyway, it's not a very easy problem, but this is a very interesting one. So hopefully the audience that want to check on the difficult problem can enjoy this one. Okay, let's just get started. The problem set is saying that in cyclic quadrilateral ABCD, BC is less than AD, CD is less than AB, and line BC and AD intersects on X, line CD and AB intersects on Y. Just stop here. So we basically know that BC less than AD and CD less than AB. This condition just defines the position of XY, right? So let's draw the circle first. Okay, this is a circle, and we want to find the quadrilateral ABCD. So this point is Y. So A, B, C, D, and this point is X. Okay. And now we know that E, F, G, H are the midpoints of A, B, C, D, A, B, B, C, C, D, D, A. So E, F, G, H, right? E, F, G, H. I'm not going to draw it here right now. We will check on this later, but let me just finish the problem set. Respectively, and angle bisector of angle BXA. BXA. We want to find the angle bisector of it. Intersects EG on S. Intersect each. Okay, let me just draw it. Draw the problem set here. So, because I want to simplify this problem, show the way that I'm thinking about it, but it looks like there's no other way around. Let me just draw it here. Anyways, okay, we find the midpoint probably look like this, and let me get the angle bisector line first. So this looks like the angle bisector line. We would have the midpoint here and the midpoint here. So for this case, probably this is a angle bisector line. So we would have midpoint actually here, right? Very close, and the midpoint here. Yeah, that's correct. Has to be this way. So this is an angle bisector line, and this is an angle bisector line. So here, this point is E, this point is F, this point is G, this point is H. It's basically saying that EG Okay, EG meets the angle bisector of BXA on the point S. And FH meets the angle bisector of angle AYD on the point T. Now we want to prove that TS is in parallel with BD if and only if, okay, TS is in parallel with BD if and only if AC, okay, AC divide the quadrilateral ABCD into two triangles with the same area. Okay, let me repeat the problem set again. So first we have the quadrilateral ABCD here, and we extend AB, DC. Of course, we have the BC less than AD and CD less than AB. That's just to point us where is the X and the Y, right? Because we want to extend the edges and find the intersection point. So we find the line AB meets line CD on Y, and line BC meets line AD on X. Now we find the midpoint of each edge of the quadrilateral, and then we connect the midpoint from the opposite edge. And this EG intersect with the angle bisector of angle AXB on the point S. And FH meets the angle bisector of angle AYD on the point T. Now we want to prove that TS would be in parallel with BD if and only if AC divides the BADC into two triangles, which is triangle ABC and triangle ADC. They have the same area. Okay, now we just have a very close impression of the figure and the problem. Now let's put this aside. Let's just consider about how can we find the breakpoint of this problem, right? The breakpoint is that on the question that we want to prove that if and only if AC divide ABCD into two triangles with the same area. So let's just start from here. First we say, oh, AC divides the ABCD into the triangles in the same area, and we want to prove that TS is in parallel with BD, and we will check on the procedure of the proof to see if it's reversible on every step, right? If that's valid, which means we already proved the if and only if cases, right? Okay, now think about the quadrilateral ABCD, right? That AC can divide the ABCD into two triangles with the same area. That is saying the altitude of triangle ABC and the altitude of triangle ADC would be the same, right? So if we this figure is too busy here, let me just draw another one here. We have A, B, C, D here, right? Think about that. If these two areas are equal, that means that means these two altitudes must be equal because AC is a common edge, right? Which means, let me just put it here. So which means if I redraw this figure, I mean, for this problem, we have to redraw it for several times because we want to put the problem to be a little more difficult. Okay, that's like we do research moving forward step by step. Okay, so just think about that. We have an AC here, right? Think about how can we find. So if we already know the ABC here, how can we find the point D so that ABC has the same area as ACD? Meanwhile, the altitude on the edge C would be equal in the triangle ABC and the triangle ADC, right? That's a question. So what we can do is that we first find the altitude here, right? And then we can find the symmetrical point here. And based on the symmetrical point, we draw a parallel line with AC, and this parallel line would meet the circle O on another point. So we know that this point has an equal distance to AC comparing to the point B, right? So let's call this D. Then we know that we can now connect the AD and extend BC. So on this point, we call it X. And for CD, right, it looks like straight, okay. And for AB, we connect it on, so this point is Y. Okay? That's how we get the figure, a correct figure first. And now let's think about the angle bisect lines here. And here. You may already notice that I put these two angle bisector to be concurrent with AC. Right, I did that on purpose. So I want to prove this first. The angle bisector of angle AYC and the angle bisector of angle AXC and line AC are concurrent. I want to prove this first. Okay. To do this, we need to just think about that they are meeting at different point. Okay. So for example, this one is at I don't know, it's a little busy again. Let's call it Q1 and so the angle bisector of angle AYC is YQ1. Okay, that's actually the angle bisector meet with AC on Q1 point. And for the angle bisector of angle AXC, let's call it XQ2. Okay, that's a point meet on the AC. We want to prove that Q1 and Q2 are the same point, right? So the first thing we can think about why I want to do this. I will explain that later. But the first thing is that if you look at this problem, we actually only have two real problem sets that we can use for solving this problem. The only two real problem set is that this altitude equals to this altitude, and ABCD is a quadrilateral. right? Now we need to think about B, this altitude equals to this altitude, right? How can we use it? How can we take advantage of it? Okay, think about that. If I want to prove that yq1 equals to xq2, because the triangle YAC and the triangle XAC are sharing the same edge AC, so basically I want to prove that AQ1 to Q1C equals to AQ2 to Q2C, right? I want to prove this one. AQ1 to Q1C equals to AQ2 to Q2C. So that's a target. And what is AQ1? AQ1 to Q1C, because Q1 is YQ1 is the angle bisector of triangle AYQ, so AQ1 to Q1C that equals to YA2 YC, right? And AQ2 to Q2C equals to XA2 XC, which means I want to prove YA2 YC equals to XA2 XC. Okay, now look at the triangle XCQ2 and the triangle, well, let's say this way. Look at the triangle XCD, okay? Triangle XCD and the triangle XAB. Okay, look at these two triangles. We know that these two, the triangle XCD and triangle XAB are similar. This is what we already learned, many times from the quadrilateral ABCD, right? So we already know these two are similar, which means I guess I need to extend this a little bit. So let's just extend the XO2 to here, right? And let's say XO2 meet CD on a point, let's call it I, and meet AB on a point, let's call it J, right? So we know that triangle XCD is similar to triangle XAB, and also triangle XCI is similar to triangle XAJ, right? How to prove that? Because the angle XCI equals to angle XAJ, right? Because this one plus this one is 180, this one plus this one is 180 degrees. So angle XCI equals to angle XAJ. And also the angle AXJ equals to angle CXI, right? So we know that triangle XCI is similar to triangle XAJ, which means AC2 actually XA2 XC equals to AJ2 CI, right? XA2 XC equals to AJ2 CI. And also equals to XI2 xj. Oh, sorry, xj to xi. Okay, equals to xj to xi. We will need this one later. Okay, we will need this one later. But let's just put it here for now. It equals to xj to xi. Now look at our target. We want to prove that ya to yc equals to xa to xc. So for here, we already know that xa to xc equals to aj to ci, right? Also, based on this one, we know that xa to xc equals to, because the triangle xcd is similar to triangle xab, so xa to xc equals to ab to cd, right? Similarly, triangle ybc is similar to triangle yda, which means ya to yc, this triangle and this triangle are similar, so ya to yc equals to ad to bc. This is saying that we want to prove AB to CD equals to AD to BC, which means we want to prove that CD to BC equals to AB to AD. Right? And what is CD to BC? CD to BC equals to sine angle CAD to sine angle BAC, right? Because ABCD is a cyclic quadrilateral, they are all on the circle O. So each chord can be calculated for the, like CD can be calculated for the 2r times the sine angle CAD. And BC can be calculated as 2r times the sine angle BAC, right? So 2r cancel each other, so we got this one. Basically, that means the CD to BC equals to sine angle CAD to sine angle CBAC, right? And because of this, we already know that this is what we already know, right? And also we know that if we connect, look at here, if we connect BD, okay, if we connect BD, and BD meets AC on a point, let's call it K, okay? Because the altitude from B to AC equals to the altitude from D to AC, so it's very easy to prove that BK equals to KD. K is the midpoint of BD, right? Because these two are right triangles, similar right triangles, and also the altitude are the same. So these two triangles are congruent. That means BK equals to KD, right? So K is the midpoint of the BD. Okay, now let's look at the area. So I want to calculate the area of BAK to the area of KAD. The ratio of the area, right? The BAK to KAD. What is the area of BAK? That is half of AB times AK times sine angle BAK, which is sine angle BAC, right? So let me just write it as C. 2. What is the area of triangle KAD? KAD. That is half of AD times AK times sine angle DAC. Right, so you can see that AK cancel each other, half cancel, so it equals to AB to AD times sine angle BAC to sine angle CAD. Right? And we already know that BK equals to KD, which means the area of BAK equals to the area of KAD. That makes this to be 1. And which means because the sine BAC to sine CAD equals to BC to CD. So AB to AD times BC to CD equals to 1. Right, we got this one. So based on this, we know that AB to AD, here, look at here, AB to AD equals to CD to BC. So we just prove it, which means we just prove that we just prove that AQ1 equals to AQ1 to Q1C equals to AQ2 to Q2C, right? Because all of these are reversible. That means YA to YC equals to X to XC. That is valid. So go back to here, right? So this is true, right? So make this target to be true. And based on this, this would be true. And this, we got this one from all of these equations. So we got this is true, right? Okay, so for now, we just prove that the angle bisector of angle AYC and angle AYD and the angle bisector of angle AXB and AC are concurrent, right? They meet on this point. Let's call it Q. So you may get curious why I spent so long time to do this calculation. Because based on this, we introduce the idea that the triangle XCD, right, and the triangle XAB, they're similar. So, and also XI to XJ, that's a ratio of the similar triangles, right? And notice this, because AB to CD equals to AD to BC, right? AB to CD equals to AD to BC. What is AB to CD? AB to CD, that is a ratio of the triangle XBA to the triangle XCD. It equals to AD to BC. That means if I extend the angle bisector of angle AYD, let's call this point as M, this point as N. So we just derived that XI to XJ equals to YM to YN. Right? YM to YN, it equals to BC to AD. Right? It equals to BC to AD. And XI to XJ equals to CD to AB. And we just prove that here CD to AB CD to AB equals to BC to AD, right? CD to AB equals to BC to AD. CD to AB equals to BC to AD. So this one is a key point. That XI to XJ equals to YM to YN. Okay, now let's get back to this problem. The problem is asking us to prove that, I think this figure is not good enough because this point should also be on the AC. I can prove that easily, but let's just use this figure for now. Think about that EFGH, right? EFGH. So EF should be in parallel with AC and equals to half of AC, and the distance from EF to AC would be half of the altitude from B to AC, right? Also, the HG is in parallel with AC and half of AC, which means that HG equals to EF. And also the distance from HG, because HG is in parallel with AC, so the distance from HG to AC, that's half of the distance from D to AC. And we already know that the distance from B to AC equals to the distance from D to AC, which means the distance from EF to AC equals to the distance from HG to AC, right? And see, EF and HG, they are in parallel and equal. That makes EFGH is a parallelogram, right? Which means EG and FH bisect each other, right? And also we know that the distance from EF to AC equals to the distance of HG to AC. That means AC is passing through the intersection point of HF and EG. So that means this point should be on AC. Okay, that's a quick proof. Just neglect that for now. Let's think about the problem that we want to find the we want to find that TS would be in parallel with BD, right? Okay, think about this point, the intersection point of F, H, and EG. Let's call it, I don't know, call it Z. Okay, call it Z. So this point is Z, and this is a midpoint of FH and EG, because EFGH is a parallelogram, right? So Z is a midpoint of EG, and Z is also a midpoint of HF, and also they should be on AC, right? It's just a figure issue, but it doesn't matter for now. Just remember that Z is a midpoint of HF and the midpoint of EG. Okay, so look at how we get the point T. T is a point, right? That is the intersection point of F, H, and Y, Q, right? I still call this this angle bisector as YQ. Okay, so T is intersection point of FH to YQ, which means if we connect YF, we connect YH, right? So we can get that TF to TH equals to YF to YH, right? Because triangle YBC is similar to triangle YDA, and F is a midpoint of BC, H is a midpoint of AD. That means YF to YH equals to BC to AD, right? Which means TF to TH equals to BC to AD. And also for the point S, it comes from the intersection point of the XQ and EG. If we connect GX, we connect EX, right? So we have GS GS 2 ES equals to GX 2 EX. And we already know that G is the midpoint of CD, E is the midpoint of AB. Because triangle XCD is similar to triangle XAB, that means the GX to EX equals to CD to AB. Right? Which means, see, we already got this one, right? BC to AD equals to CD to AB. See here and here. BC to AD equals to CD to AB, right? That means TF to TH equals to GS to ES. Okay? So GS, TF, see, TF to TH, right? And if you think about the point Z here, because Z is a midpoint of HF, right? So for here, for this one, we can do this. TF to TF plus TH equals to GS to ES plus GS, right? So we get TF to HF equals to GS to EG, right? And we can get TF to half of HF equals to GS to half of EG, right? So which means TF to, what is half of HF? Half of HF is ZF. So TF to ZF equals to GS to half of EG. That's ZG. Right? See here. Let me just draw it again. So it looks like this. This is Z, this is T, this is F, and this is S, this is G, right? So TF to ZF equals to GS to ZG. That means TS is in parallel with FG. And we already know that FG is in parallel with BD, right? Because F is the midpoint of BC, G is midpoint of CD, which means TS is in parallel with BD. Okay? So we just prove that if AC divides the quadrilateral ABCD into two equal area triangle, then it is true that TS is in parallel with BD. So how can we prove that if TS is in parallel with BD, it's still true? See, if TS is in parallel with BD, then TS is in parallel with FG. Then all of these are valid, which means we can derive back to this equation that CD to AB equals to BC to AD. And if you want this to be true, then this has to be true, right? This has to be true. If you want that to be true, this has to be true, which means we can eventually get the answer that the triangle area of triangle BAK equals to the triangle area of triangle KAD, which means the area of BAK equals to the area of KAD, means K is a midpoint of BD, which means that the distance from B to AC equals to the distance from D to AC, which means the triangle ABC and triangle ADC has the same area. Okay? So I really appreciate the audience. This is a problem I quote from Indonesia. I think this is not a very easy problem, but it's a very interesting one. And I hope you enjoy the video. I hope this would be clear to you, although the figure is like a mess, right? Because it's difficult to draw this figure. So you can put it in the GeoGebra to check it out. But basically, the idea is here. Okay, I hope you like this video. See you in next one. Thank you.